So it's a great pleasure for me to introduce Jacob Diamond. Jacob is a doctor in hydrobiology. He has done his master studies at the University of Florida in ecohydrology in 2013. And then he realized his PhD at Virginia Tech in forest hydroecology in 2019. In between, he has been an environmental consultant at Salt Lake City in Utah. And for the last 2.5 years, he has been here in Lyon with us, and he's a postdoc with Florentina Moitard from the Riverly unit in Lyon. And his research project has been financed by several entities. First of all, with the Agence de l'eau Loire Bretagne, and then he has got a grant from the H2O'Lyon, as it was just recalled. And today is financed by the Agence de l'eau Rhône-Méditerranée Corse to work on the Ripoxy, and this is a part of the project that he will present now. So I don't want to be much longer, and I give the floor to Jake for his presentation, and then I will come back for the questions later on. The floor is yours, Jake.
Thank you, Gilles. Thank you very much. So good evening, everybody. It's a real pleasure to be with you here at H2O'Lyon, this webinar series. As Gilles introduced me to you, I'm a researcher engineer currently working at INRAE, but most of the work that I'll present to you today was done under contract with the Université de Tours and CNRS. And I'd also like to thank the funding sources at H2O'Lyon, Université de Lyon 1, and l'Agence de l'eau Rhône-Méditerranée Corse for financing and facilitating the scheduling and the conference, the webinar today. So I'm going to share with you today some work that we've been doing over the past 1.5 years focused on dissolved oxygen in flowing waters and how we can use those measurements of dissolved oxygen to make ecological inferences. I'll also now acknowledge my collaborators and co-authors, Drs. Florentina Moitard, Gilles Pinet, Matt Cohen, David Lewis, Alain Proel, Cécile Martinet, Anthony Maire, and Susanna Bernal. So because we can't go to the restaurants right now, I'd like to present to you with a full 3-course scientific menu with entree of water and a gaseous oxygen pairing, a plat of regime shift analysis with a side of metabolic processing, and to finish a layered cake of network patterns and nonlinear behavior. Bon appétit. So because we have a very diverse group of attendees, and just to make sure we're all on the same page, just to tell you what dissolved oxygen is, it's just that. It's just the amount of dioxygen molecule that's dissolved in solution. So I know I probably don't have to tell the H2O'Lyon webinar that dissolved oxygen is important because all organisms require it. It's therefore a measure of water quality, and we can use it to say things about what's happening in aquatic ecosystems as well, which we will see soon. Just to give you some context, the first part of the work I'm going to show you is really focused on the Loire River basin. It's the longest river in France, as most of you probably know, and is often referred to by multiple sources as one of the last wild rivers in Europe due to its minimal influence from dams along its main course. So our understanding of dissolved oxygen in the Loire River basin began in the early 1970s, a trend which is largely mirrored in other industrialized river basins. I'm showing here on the left the average summer dissolved oxygen values in milligrams per liter for all the known stations from 1970 to now, with the years going up here. And on the right, I'm just showing you the number of sites where dissolved oxygen was measured in the French National Water Quality Database. So we see a really large increase in the number of sites starting in the 1990s here, when in 1992, when the Water Act was passed and the Ministry of Environment was given a lot more resources. But the general point I want to make is that our understanding of dissolved oxygen, or I might call it DO sometimes, is kind of a recent thing, the last 40, 50 years or so. So today I'm going to concentrate mainly on 2 regions to explore the variability in dissolved oxygen and its ecological implications. The first is in the middle Loire between Nevers and Orléans. And then later on, I'll talk a little bit about some headwater network sites we have in the headwaters of La Loire in the Forez region. So what controls dissolved oxygen concentrations in aquatic ecosystems? So here's the Loire River basin. You may be able to detect some spatial patterns here in the average annual minimum concentrations for every water quality station in the French database. Maybe it's getting a little, the lighter colors are very low oxygen, the very dark colors are very high oxygen. But why is that? Why does it look this way? Excuse me. So as shown on the first slide, DO is partially controlled by air, water, gas equilibrium processes. We saw that little cup. But also hinted by the short clip that I showed after, dissolved oxygen is also heavily controlled by something we call stream metabolism. But what is that? Here I'm showing some daytime conditions in some idealized stream. So solar radiation is increasing the air temperature and the water temperature, and it's also driving photosynthesis in aquatic autotrophs. These autotrophs are just like land plants. They convert solar energy, water, and carbon dioxide, here we call it inorganic carbon, into reduced carbon compounds that are then used to sustain life, releasing oxygen as a byproduct. We measure this efficiency as something we call primary productivity or gross primary productivity, so GPP. Then the collective dissipation of this organic energy that the plants are storing from sunlight, which is consumed by the plants themselves and also heterotrophs, we call respiration, or in this case, we call it ecosystem respiration because we can't tell where it came from. All we can do is measure the overall influence that all of these consumptive processes have. So taken together, GPP and ER, production and respiration, are the fundamental metabolic rates of ecosystems that constrain the energy supply and dissipation in the food web. So in the daytime, production is greater than respiration, so we have increases of oxygen in the water column. In contrast, at night, photosynthesis ceases. So now we have respiratory processes are dominating because there's no photosynthesis going on. So GPP is essentially zero, and we're consuming oxygen to eat up the carbon that the plants have made and other carbon that's in there too. And all the while, because we're in a river or a stream, things are moving downstream. So in 1956, named H2O'Lyon made a very important conceptual advance where he realized that the shape of oxygen time series can actually be used to tell us the relative rates of production and respiration. I'm not going to tell you exactly how we do it, but we can. And we can also consider, therefore, the balance between production and respiration, which we call net ecosystem production. So if you have a positive value of this, it means the system has a net increase of carbon and a net in biomass, and therefore a net increase of oxygen in the water column, and the reverse is true if it's negative. Okay, so ecosystem metabolism is a very important, it's an inherent measure of the energetic capacity and efficiency of ecosystems. So it basically, it's just the fundamental building blocks of ecosystems. So it's really important for us to understand as ecosystem scientists and environmental managers, this fundamental building block. And I think it's really nicely illustrated here in one of Odom's original works, where we have sunlight coming in, being transformed by plants into organic energy, which is then moved throughout the food web. All the while, we're losing energy to entropy and respiratory processes. And more recently, so metabolism in ecosystems has been pretty well measured in terrestrial systems for a long time, but only recently have we really started as a community studying it in flowing waters. And these measurements, we think, are going to be very important for setting water quality expectations, restoration targets, and designing monitoring programs. So what do we know about ecosystem metabolism, primary production, and respiration? Well, we know that GPP is largely a function of how much light is available, as well as a few other things. You can imagine here that in this stream in the bottom left has a lot of light available for the autotrophs to turn into carbon, releasing oxygen into the water column. Maybe here on the right, not so much. And in contrast, we know that respiration is largely a function of the amount of carbon and the quality of the carbon, which is the C here. So carbon can come from the autotrophs in the stream. It can come from the terrestrial environment, from leaves or from soil organic matter. And and temperature also affects this as well. So we know quite a bit about the controls on these things. But what we don't know very well, and what we're starting to study now as a community, is we don't really know how do production and respiration partition into and from different organisms. So for example, when we measure the oxygen in the stream, we don't know how much of that oxygen came from a macrophyte or an algae or phytoplankton or benthic plankton. And then we also don't really know, after the carbon is created, who is eating it and to what extent they're all eating it. So this is an open question. We also don't know how metabolism scales at the river network. So we've done many studies on little reaches, 100 meters, 200 meters, things like this. We understand metabolism at that scale, but we don't understand metabolism at large river network scales. And we're starting to understand, but still there's a lot to learn about how the ecosystem metabolism couples to nutrient cycles on the course of days and annual cycles as well. So we know that autotrophs need nutrients to create biomass, but the timing of when they take nutrients from the water column, this is all kind of cutting edge information. And finally, I think this is really important. How can we use these measurements to assess river health? This is, I think, entirely unknown territory. And so in the presentation that follows, I'm going to try and at least hit each of these and show that we're working towards these goals right now. Okay, so now on to the main course, where we ask the question, how did a regime shift, which I'll describe, in primary producer community affect metabolism and nutrient cycling? And was the shift predictable? This is something that we addressed in a manuscript that was just accepted, but it's too much for this talk, so I'll skip that. So when I say regime shift, I'm referring to how ecologists use the term, which means a large, abrupt, and persistent change in the structure or state, I'll use that word a lot, state of the ecosystem. So people have been studying regime shifts in ecosystems for a very long time. And what we find is that when you have a shift in a system like this, that I'll describe in a second, it's usually because you have really strong internal feedback processes that want to maintain a system in one state or another. So the Middle Loire underwent such a regime shift in the past 15 years or so. For most of the 20th century, the Middle Loire looked much like this pea soup picture here. Freshwater ecologists would probably call this a eutrophic state, which has a lot of algae and phosphorus, a lot of chlorophyll, turbidity, low water clarity. And then relatively suddenly, in about 2005, the ecosystem abruptly shifted to a predominantly clear water state with low algae, low phosphorus, clear water conditions, but also this increase in a filter feeding clam, Corbicula fluminea, and also this emergence of these macrophytes, these submerged plants here under the surface. And so we can not just see this with our eyes, we can look at the data as well. So I'm going to walk you through this figure. It's a lot to see. This is a time series starting in 1990 and ending in 2018 of many different water chemistry constituents, but really let's focus on chlorophyll A here, the Corbicula clams, and macrophyte cover in percentage. Note the Corbicula is on a log scale here. So the vertical dash bar here indicates a change point in the time series, which we can calculate with some statistics, where we're going to call this change point a regime shift in ecosystem state. So we have one state here of high chlorophyll and one state here of low chlorophyll, for example. The panels on the right then show the mean summertime values of each of these states. So for example, in the eutrophic state of the Middle Loire, we had 0.08 milligrams per liter on average of chlorophyll A, afterwards 0.01. So I really want you to note that chlorophyll A decreased by essentially an order of magnitude, about 90% between these two states, and it was extremely abrupt. It wasn't like a smooth decline, it happened quite rapidly. And we see similar things from all other constituents as well, including phosphorus. So the occurrence of such an abrupt shift is kind of interesting in rivers. It's not commonly observed. So this type of shift in aquatic systems is really commonly seen in lakes. There's been a lot of studies of how ecosystems can shift between eutrophic to oligotrophic clear water states in lakes. But it doesn't happen much in rivers because rivers don't have a lot of strong internal feedbacks. Water is always moving by every year. It's flushing and changing the state and moving things downstream. Whereas in lakes, you have this long residence time that can allow for processes to kind of develop internal feedbacks to develop. However, recently there has been another system, the Ebro River in Spain, that exhibited a similar shift to the Loire. And so to me, I think this is actually quite unexpected. And I think it's an interesting case study for understanding that how feedbacks can develop in ecosystems as well, in river ecosystems as well. But we need to check. I mean, it's easy to talk about alternative stable states. It's kind of a sexy term in ecology, but it's complicated to test and it's complicated to statistically analyze. There's as I mentioned, there's a well-developed body of theory and empirical evidence. Theory kind of shown here on the left for what happens in lakes between alternative stable states. So one of the classic expectations is this S curve. So briefly, we can imagine a lake with very low nutrients, this blue line here on the left. And let's say we start adding fertilizer and the nutrients are increasing, phytoplankton are starting to grow, increasing the turbidity or decreasing the clarity of the water. And at some point, you reach this critical concentration of nutrients that creates a critical concentration of turbidity or water clarity that abruptly shifts the system to a state now dominated by phytoplankton. So here we had macrophytes, clear water. Now we're dominated by phytoplankton and there's no macrophytes. So do we see this behavior in the middle Loire? I would argue that we're seeing a weak form of it. So I'm showing here chlorophyll A versus phosphorus and TSS, which is like turbidity, versus phosphorus as well, so like a nutrient. And these are colored by very dark values being the early years and very light values being the most recent years. And so I think we are seeing a similar shape to the curve. We're seeing kind of a clustering here and a clustering here, indicating these two stable potential states of ecosystem state in the middle Loire. But what I really think is cool about this curve is that we're actually seeing the path backwards along this curve. Typically, most studies and most empirical or theoretical modeling looks at ecosystems that go this way and jump to the phytoplankton state. We're seeing this way where you have to go reduce nutrients by quite a lot to jump back to this clear water state. So I think we have some evidence that that we observe alternative stable states in the middle of Loire. We looked at other ways to look at this data, considering the Corbicula clams as a major driver of the change as well. But I'm not going to get too much into that right now. We can talk about it in questions. Okay, so the point of this talk is about oxygen and what we can learn from it. And this is why I said I'm not really comfortable with the terms oligotrophic and eutrophic with rivers anymore, because those terms were developed for lakes, and implied in those terms is for a eutrophic lake, you have very high productivity, and an oligotrophic lake, you have very low productivity. But when we use this amazing 30-year data set of hourly dissolved oxygen, which is just amazing, we did not observe this behavior. So we calculated metabolism, we calculated GPP and ER from the oxygen data. And we were really expecting to see, with this change in regime, I mean, a huge change in phytoplankton, complete loss, that something would change to metabolism, but we saw nothing. I mean, it's remained essentially constant throughout the entire period. And where we could detect a change point, this is exactly like the other figures I showed you before with the time series, where we could detect a change point, the values after were 10 to 20% different for respiration and production, not the order of magnitude change that we saw for the ecosystem states. So I'll emphasize again that there was no obvious link between a state regime shift, so the state variables being like phosphorus, chlorophyll, turbidity, things like that, and a process regime shift, so GPP and ER. So this is illustrated here in these right two panels. So we have production versus chlorophyll and production versus phosphorus. So to put it slightly differently, chlorophyll A is a standing stock or a biomass or state that did exhibit an abrupt and large regime shift, but GPP is the amount of work that the biomass is doing did not exhibit this behavior. In fact, you can get the same GPP at wildly different value. This is log scale of chlorophyll A and wildly different values of phosphorus. And I'd suggest that this is pretty relevant to some recent calls for using ecosystem metabolism to guide restoration efforts. So, you know, if the management goal is clear water, looking at ecosystem metabolism may not tell you that much, at least in this case. And there's been some recent evidence too that suggests that this is not unique to the Loire River, that actually processes in ecosystems are resilient to changes in their structure. So I think that's a pretty interesting finding, that these ecosystems continue to process materials at the same rate, regardless of who is there, regardless if it's macrophytes or phytoplankton. Very interesting to me. So I don't want to leave you with the idea that the color of the river changed and nothing else. When we looked a little more carefully, we found that there were some clear changes to ecosystem processes. I mean, we can see it with our eyes, something must be changing. The first is that the temporal coupling between production and respiration weakened, okay? This is a little complicated to describe, but temporal coupling refers to the speed at which the carbon fixed from the atmosphere by autotrophs is then respired as CO2 back out into the atmosphere by the ecosystem. So for example, in the phytoplankton state, the carbon produced is really tasty for organisms, and it's right there in the water column. It's very easy to access, so it gets turned over very quickly. We would call this a very tight coupling of GPP and ER. And we can actually assess this coupling with some kind of test. It's not important really right now what it is, but the important thing to know is if the values are below this line, there's a very tight coupling between GPP and ER. And right around the shift of production and respiration, we have a weakening of this coupling. Someone's at my door. Okay, the second thing that we find is that the relative changes between production and respiration were not exactly mirrored. So the GPP magnitude was reduced slightly less than respiration. So GPP here was a little bit bigger than ER, but in this new state, GPP is actually a little bit less than ER. So we had those slight changes, but they didn't change completely in balance. And what this means is that the middle Loire transformed from a net sink of carbon, so carbon was being sequestered by the system, to a net source of carbon in this new regime dominated by macrophytes. And the third important thing that I want to leave you with was that there was a relative shift in in-stream processing for carbon and nitrogen. And we can assess this with by looking at basically the ratio of how much carbon is removed by the system versus how much is transported downstream, and the same with nitrogen. So that we can take that ratio and look at it. And basically what we find is that we have large changes. So in the phytoplankton state, nitrogen transport was quite low compared to how much was stored by the biomass. And carbon transport was quite high because there's a lot of phytoplankton which are just being transported downstream. And these completely flipped in this macrophyte dominated state. So we have very little nitrogen transport, or very little carbon transport downstream relative to this state, and a lot more nitrogen transport. So this regime shift had a lot of impacts on ecosystem processes. It just was not a huge change to production and respiration magnitudes per se. So to sum up this main course here, I think we have confirmation that large synchronous shifts across state variables can occur in rivers with abrupt transitions to new resilient states, but that despite these massive shifts in ecological state, the metabolic regime, so production and respiration, changed far less and far later, so it didn't happen at the same time. Finally, as macrophytes replaced phytoplankton as the dominant primary producers, production and respiration decoupled, that temporal decoupling I mentioned before. We became from a carbon sink to a carbon source. And also we had this diverging response of carbon and nitrogen, how much is being transported versus how much is being processed in the river. And I just want to mention again that all of these inferences that we made here were based on the analysis of dissolved oxygen signals. So it's kind of incredible to me that dissolved oxygen can really do some serious work when it comes to our understanding of flowing water systems. Okay, so moving on to the dessert here, where we focused on understanding dissolved oxygen dynamics at the network scale. So I mentioned that's kind of one of the things that we don't really understand well about metabolism and oxygen and river networks is the scaling of it. Someone's trying to get in my door. So for this, we went to the headwaters in the Plaine Forez and we looked at 40 different sites with varying land cover and arrangements. So over the past year and a half, we sampled 40 sites in the Forez region, some on the west side, some on the east side, with differing ways of storing water. Some store water in streams, some store water on ponds in the landscape. Wide range of catchment areas. Excuse me, I forgot the cheese. So in preparing for this talk, I went down a little rabbit hole on the history of dissolved oxygen measurements, which I'll share with you briefly. So the first instance I could ever find in the literature of measuring dissolved oxygen was in 1859 by someone named W.A. Miller, who wanted to know the gas composition of the River Thames in England. So he used this instrument called a pneumatic trowel, where you boil some water here, the gases come up and get caught here, and there's some mercury here. So the amount of mercury that gets displaced is your total volume of gases. And then you can see what the gas is made of by using some kind of reagent. Here for carbon, it's pyrogylate of potash. And I wanted to share you with the results of his analysis, because I think it's really fascinating compared to how we think of now, published in 1889. He says, undoubtedly, the Thames water owes its deficiency of oxygen to the reducing action of the urea and other matters poured into the river in the form of sewage, which is exactly what we know happens now. And starting from this fact, an attempt has been made to raise through aeration as a sort of standard of purity. Very little practical use can, however, be made of the state of aeration, since the purest deep spring waters are also liable to imperfect aeration. And in this respect, the very best and the very worst waters are on par with one another. I'm not sure about the last point, but it's very interesting. I mean, 130 years ago, thinking about this and doing quite a good job with measurements as well. And briefly, people started improving on these methods. So they found a way to do a colorimetric method where they could actually figure out how much oxygen was in people's blood, which is kind of fascinating. This was developed by Schutzenberger. And people started improving on this, and really all kind of iterations of the same colorimetric method. And I wanted to present some results from H2O'Lyon, who also did some research on the River Thames using a similar method. So as far as I can tell, the River Thames has the earliest measurements of dissolved oxygen of any river on Earth, which is pretty cool. So using this apparatus, he found the well-observed oxygen, the decrease in oxygen that we see when you have sewage coming into the river. But he says this: much more might be said regarding this process and its applicability to water analysis, in which I am at present engaged, but I have already detained you too long and can only express a final hope that other members of our society will take up this extremely interesting subject and bring their experience before us. So I'm happy to say that we're carrying the mantle of this extremely interesting subject of dissolved oxygen in rivers. Okay, so people made some improvements over the next 20 years or so, but nothing too interesting, until finally this big change in 1888, developed by Ludwig Wilhelm Winkler in his dissertation, which is called Winkler titration. And for the next 70 years, this was the most commonly used method for dissolved oxygen measurements. Fast forward to now, and we have these in situ optical dissolved oxygen sensors that can record extremely precise measurements, like up to 0.02 milligrams per liter precision at up to 1 minute intervals. We installed these in all of the 40 sites that I previously mentioned and housed them in PVC to protect them. And just to give you a flavor of the type of sites we're working in, they vary quite a lot in terms of their surrounding land cover, their substrate, their width, their shading, their light availability, and their depth. So here's a typical view of the type of landscape that drains to these streams, which is quite pastoral, and the types of autotrophs that exist there. So you can have these long filamentous algae, and you can have these kind of macrophytes as well. So quite diverse sites. So I've talked a lot about what we can learn from dissolved oxygen, but I don't think I've shown you an example time series yet. So this is what it looks like when we we download the data from the field, we bring it back to the computer, and we plug it in. This is a time series from early spring at one of our sites. where we're looking at dissolved oxygen, and green is the metric is percentage of saturation. So if it's at 100%, it's basically perfectly equilibrated with the atmosphere. And if it's not 100%, then something is acting on it. Something is producing oxygen or consuming oxygen. And in blue, we have temperature. And so what we see is early on in the year, it's pretty much at saturation. There's not too much going on. But as the days start getting longer, the temperature starts warming, we start seeing this production signal, increase in oxygen during the day, increase in oxygen, and it's increasing over time. And then at some point around April 20th, we had a rain event. So during that time, the river can become quite cloudy. There's no light penetrating, so primary producers can't produce oxygen. And a lot of carbon can be brought in stirred up from the bed of the stream and also brought in from the landscape, which increases respiration. So we have this drop in oxygen, which we see at our sites regularly, sometimes going hypoxic, in this case almost. And then after that, we have some recovery period. The stream's coming down and it's moving back up to equilibrium with the atmosphere. But at this point, unfortunately for the autotrophs, the leaves on the trees had now come out and were shading the stream. So there's no light available for the productivity of production. So actually, the autotrophs in the stream had a very short window to do their thing. So I mentioned that we were interested in this idea of network behavior, and I'm just showing you 4 nested sites in one of the watersheds we looked at, and a time series of each of these sites. So we're looking, do we see evidence of some kind of network behavior? We have many sites, more sites, but I picked these 4 because they were kind of exemplary of the type of patterns we might see. So is there a clear upstream downstream pattern? Based on what we've looked at so far, it isn't very clear, at least when you just look at oxygen by itself. While we do see a reduction in the daily minima, so this yellow is the most downstream, so the minima are these low points here that happen in the middle of the night. We see the reduction, so decreasing daily minima as you go downstream. Other patterns are not so easy to discern. For example, the 2 sites in the upstream part of this watershed, the light green being the most upstream and the blue being just downstream of that, about 100 meters. These ones here have completely different amplitudes than each other, and they're only 100 meters apart. So they're not really fitting nicely into this upstream downstream pattern. So maybe there is some network behavior, but it clearly can deviate depending on certain other factors. I think the most obvious one is where the local scale controls on dissolved oxygen. So for example, here's that downstream site in purple and a further downstream site, a more upstream site in purple and a further downstream site in yellow. We're seeing a little reach of the river here and land use surrounding it in a 200-meter buffer. And the same dissolved oxygen time series here. So there's a clear difference in land use here. The upstream purple one has much less forest cover around it, so it has the potential for more light availability and therefore production potentially. It's surrounded by agriculture and urban areas which might contribute nutrients to the system. Whereas this yellow site, the further downstream site, is covered by forest along its entire length, reducing light availability. So potentially this would have less production. I don't know if we see that because really it's the amplitude, the range in min versus max that tells us something about productivity, and they have similar ones. But maybe there's something else going on too, another layer of complexity. So when we were out doing site selection, we became really interested in this idea of confluence behavior, thinking about confluences as their own sample unit, because confluences are basically nodes of a graphical network. They could potentially be a really useful framework for thinking about river biogeochemistry. We noticed that some confluences joined waters of extremely different chemistry, for example, here, order of magnitude difference in chloride, which led us to wonder if downstream mixing of 2 different water chemistries would lead to some kind of unexpected behavior in production or respiration and ecosystem metabolism in general. So I'd call that, if there is some kind of effect, we would call it non-conservative. So otherwise, if the waters are just mixing, if it's just oxygen 5 here and oxygen 10 here and downstream it's 7.5, that's conservative, that's mixing. But we have to kind of check this out first. It was an intriguing idea, but we didn't really we needed to test ourselves, make sure we understood that how a good way to think about this, a good way to look at it. So we started looking at a few of our confluences. I'm showing you two examples here. One is this very small confluence with a forested area here, and another is a very large confluence with a lot of agriculture surrounding it. So this one is here, and this one is here. We see two time series. So the blue solid line is always the downstream, and the dashed lines are the upstream ones. So we can ask ourselves, just to check, is it even possible that there's this non-conservative behavior? We can ask ourselves, is the downstream dissolved oxygen signal constrained by the upstream signals? And one way to do this is to focus just on the maxima and the minima of each day. So is the maxima constrained within these two downstream? Yes. Is the minima? No. Every single day it's lower than the upstream values. And what about for this one? Every single value is not constrained within the two upstream reaches. So there's something else going on besides just mixing. So this gave us some confidence to start looking at this a little more carefully. And one way we can summarize all that data, so I showed you two confluences, and then here I'm showing you all 10 that we had for these initial sites. And we can summarize it by saying, okay, every day that we have data, we can go and we can say, was the downstream maximum within the range, below the range, or above the upstream range? And we can say the same thing for the minimum. So for that small confluence that I showed you before, we can see that every single day, the minima is basically below the upstream minima. So the black, the downstream minima is below the upstream range for the majority of days. And really what we can, just to simplify understanding this figure, is just compare the colored area with the gray area. And what we see is that for most days at most of our confluences, we have some kind of non-conservative behavior. And we don't know exactly what's going on yet, but this is, I think, really interesting and gave us a lot more confidence to also to pursue this idea. And we could summarize this even a little bit more by, for each day that we see non-conservative behavior. So when the downstream oxygen signal is not within the upstream ones, we can say, okay, what's the difference between the maximum and what's the difference between the minimum? So the black is the minimum, the green is the maximum. This is the percentage difference. And so what we see is that for most of the days where we have data, when the downstream maximum is higher, it's not by much. It's just by 10% or less, usually less than 5 or so. However, when the downstream minima is less than the upstream, it can be by quite a lot, 10, 20, 30%. So maybe this means that we have some kind of priming effect. If you're bringing in carbon from one confluence and you're bringing it into a system that needs carbon, maybe you're priming some respiration. We don't know. But we're studying and we're really interested to keep working on this idea. So that being said, that's the focus of a lot of our future work now. That's actually in the Rhone catchment. We have 12 confluences that we've instrumented specifically to kind of look at these questions, and also effects of hypoxia in these streams. We have 6 in Lisron, and we have 6 in Lardière, and 7 in Lardière, actually. And we're really trying to answer this question: are there really these confluence effects on dissolved oxygen and stream metabolism? And we're working with colleagues here at INRAE too to look at the communities that develop upstream and downstream of confluences. We're getting some data actually this week that we're really excited about. And if there are these effects, what are the types of effects? What are the magnitudes of effects? Are we talking 2% changes, 10% changes? How do those changes add up when you scale to the whole river network? So these are the types of questions that we're working on now on the funded by l'Agence de l'eau. And we're also really interested in characterizing these confluences with kind of their anthropogenic influences and their geomorphic controls, so that we can then predict in the future what the expected confluence behavior might be, and also how DO signals will propagate at the network scale. And with that, I'd like to thank you for your very kind attention, and I'm happy to take any questions you might have.
Thank you very much, Jacob, for this nice overview of what can be done with oxygen measurements. So I already see 2 comments and 2 questions in the chat. So there is one from Bernard Clément. So you showed some development of Corbicula from 2005 in the case of the Middle Loire study. Could this population have played a role in the ecosystem respiration?
Excuse me. Yes, I think so. I think also, unfortunately, we don't have good estimates of their biomass. We just have their aerial density. And when I was looking in the literature, it's kind of hard to estimate their biomass, their carbon biomass. But I think that would be a really good way to estimate their effect. I think they had a big effect on the amount of nitrate that was in the water and ammonium, because we see a kind of I think it's a combined effect of them, going to the bathroom. I don't know why I can't think of the word right now. And also the combined effect of that and the fact that macrophytes have a much different stoichiometry of carbon and nitrogen than phytoplankton do. So they don't, and they also don't take nitrogen out of the water column. But anyway, to answer your question, yes, I think that Corbicula certainly affected the respiration balance of the system.
So there are many more coming up. So there is one from Björn Wiesel. After the shift to macrophytes, a large proportion of DO may be released as bubbles. How this impact your ecosystem metabolism calculation?
Great question. And also not only that, but some of the plants, their leaves are above the water surface. So not all of the plants are submerged. So I think we might actually be underestimating metabolism in some of these cases. So potentially the change in metabolism isn't even there. We could just be underestimating it. But to answer your question, we don't know that amount, and I don't know how to estimate it very easily. But you're right. That's an important point.
So about the Confluence work, Emmanuel Mignot was asking about, on your talk about upstream, you mean some of both inflows, right? This Confluence non-conservation of DO is odd. That's the comment actually. So can you comment on that?
Could you read it to me one more time, Gilles?
Well, sorry. So that basically he wants to make sure that when you talk about upstream, you mean the sum of both inflows. And I think I can say right. And then his comment is that this Confluence non-conservation DO is odd. That's the comment.
I agree. It is odd, and I think that's the fun part of it, is that it's odd, and we're trying to figure out why it's odd. I think it's unlikely that there's a non-conservative effect that increases productivity, because it's really just limited by the light availability. So maybe some confluences, they widen the stream, and so there's more light available locally, which could increase productivity. But that's not really an effect of the mixing of the waters. However, I do think it's very possible and likely that the mixing of waters can prime respiration, so can increase the amount of oxygen consumed by the community just downstream of the confluence. But yes, we're taking into account conservation of mass, and also the exchange with the atmosphere, which can change as well, because that depends on the depth and kind of the turbulence in the stream. So it's a complicated question, but we're excited to work on it.
One more for Emmanuel before I get to Stefan Strofek, because it's on the same line, and it will answer part of Stefan, is what's the distance between upstream and downstream sections that we are considering?
For the confluence work?
Yeah, to make sure that when we take the downstream point, where is it from the upstream?
We make sure that it's about the distance, a little further than the mixing distance of the two streams, which you can usually use a rule of thumb. It's about 10 times the river width, although it depends, of course, on the angle of the confluence and the slope of the confluence, how fast they mix. But the answer to the question is it depends on the confluence, but it's past the mixing zone.
And related to that, but the other side of the coin is from Stefan Strofek is, given that you have an increase of respiration downstream the confluence, how long this local effect can be perceived?
I don't know. But it's kind of it's an interesting question though, because it's a local effect, but then it just becomes the river. So it's just the respiration of the river at that point. But you can have all of these additive effects downstream. So I don't know to consider it a local effect or to consider it kind of an accumulation of effects. But it's a good question. I don't know.
But one point maybe that that we can also mention is basically in between two confluences, there is not so much room, and especially in small streams. So you're quickly from downstream from one confluence to the next one. So it's the length of stream that is left is in the end not very much actually.
Good point.
There's a question from Pascal Bray. Did you work also using flux rather than concentration at confluences?
Yep, and that's something that we're doing a much better job of this time around. So at our new sites. But yeah, that's critical to consider the mass balance, not the concentrations. However, again, the data that I showed before was just to see, is it even possible that there's something going on? Right now, we're doing a lot more work of doing the quantification and of the differences and doing a much more rigorous job of that.
Can you say how you do that?
Well, you use a mass balance. So discharge times, there's many ways, but you can also consider, you can compare conservative solutes. So right now we also have some conductivity probes, which is generally conservative, at least especially at that spatial scale. So we can say, we know that this solute is behaving conservatively, and what is the difference between that and oxygen? And we're also looking at developing a model, a confluence model, to understand this a little bit more as well.
So I have two questions, one from Bjorn. Did you measure any gas such as N2 or argon to see if different upstream and downstream in DO are impacted by metabolism or physical effects such as turbulence?
We did not. We did not. But it's sure that turbulence will increase it will basically, the more turbulence you have, the more it will dampen the signal. It will dampen the oxygen signal, because it basically brings it into equilibrium with the atmosphere. But no, we didn't measure that.
But if you have very low, at the end, as a result, a lower oxygen concentration, that cannot be due to the effect of the turbulence, right?
I guess it depends on, for our streams, no, but I can imagine a system where you have two streams that have very high production, so they're much higher than equilibrium. In that case, you could lower the value by having more turbulence, but in our streams, no, I don't think it's very likely.
So Emmanuel is still holding your calf, and about the methods. So he's asking, when you take a single measurement point and extrapolate over the section, assuming a uniformly distributed DO concentration, could it be the error? Did you verify the homogeneous distribution over the downstream section?
No, we didn't. But for each case, no, we didn't. But I've been working with this data a lot now, and in these streams, I mean, 100 meters, dissolved oxygen doesn't change that much. I mean, unless something is acting on it, which in this case is these confluences, but and you can measure across the width too. Our streams are quite well mixed, but it's a good point, and we need to make sure that we clearly
and he's adding that
clearly assess them.
10 width seems very low to reach. Oops, sorry. Oh, it's too fast. 10 width seems too low to reach perfect mixing.
I think potentially in very large rivers, that could be true. Although that rule of thumb value comes from a large river study from science, I don't know, 20, 30 years ago. But I think in our rivers, it seems to work well. We've also tested with conductivity measurements too. It's quite clear that it's mixed at those lengths.
There is a comment from Susanna Bernal who says that she enjoyed the meal, but so she's asking, when would you expect the highest difference between upstream and downstream sites? Analyzing when difference magnified might be helpful to understand what is going on.
Yeah, I think our initial idea was that we expect the biggest differences when there's waters of very different chemistry, which also probably means they're carrying different communities and current, like bacteria communities and yeah, different communities that do the work of respiration. And when you mix those things, there's possibilities for priming effects, I think. So my expectation is that it's the confluences that join together that are of roughly similar discharge, but with very different chemistries that we see the biggest differences. And so we've chosen the confluences that we're looking at to kind of span the range of different types. So very large main tributary and a small confluence, similar sized ones, ones up in the headwaters, ones down further downstream, ones with different chemistry, ones with similar chemistry. So hopefully we have a wide enough range where we can start addressing exactly that question: is where are the differences most striking, and are they actually important for river systems to consider?
Maybe one last question from me is that, as always, when there is a nice meal, we never show the kitchen. So there is a lot behind the scene, and in order to measure or to calculate GPP and ER, we really need to have very nice data set of oxygen, and it's even often not the case. So what would you suggest in terms of how can we use the oxygen concentration per se? Would it be already a good indicator or not? Or do we really have to go through the meal of calculating the coefficient of reaeration and all that kind of nasty stuff to make some sense with that oxygen concentration?
It's a great question, Gilles. Thank you. I think there's a lot of opportunity to just use the oxygen signal itself without having to do all these calculations of production and respiration, all these things. And you can get very similar information without having to do all of the, as you said, the dirty kitchen work of these calculations and a lot of assumptions. I forget who it was mentioned about heterogeneity. What we're finding now, I think, and hopefully submitting soon, is work just on that, thinking about how to use dissolved oxygen just in and of itself, and simple metrics like what's the range of dissolved oxygen in a day, what's the minimum value, to get at those kind of similar ideas, but without having to do a lot of work, which I think could be really useful for managers especially.
Well, I think most people, I mean, many people thanked you on the way, by the way, so I'm not recalling. So my turn to thank you, Jake, for that nice presentation. Thank you, everybody, for attending that meeting.